Hello, everyone. Today, I will present our CVPR paper, How Far Can We Go with Synthetic Data for Audio-Visual Sound Source Localization? It is selected as highlight paper. This work will be presented during the afternoon poster session on the second day of the conference, and we would be happy to see you there. Sound source localization aims to identify sound-emitting objects or regions in a visual scene. It has evolved from a subtopic of audiovisual learning into an independent research field with its own tasks, benchmarks, and methodologies. In self-supervised sound source localization, the main objective is to learn the natural correspondence between audio and visual signals from the same video. Although sound source localization has made significant progress, several major challenges still remain. One major issue is that uncurated training data often contain misalignment between images and audio. This happens because training images are usually extracted from the middle frame of videos without considering semantic relevance, as shown in these examples. However, highly controllable synthetic data generation can help reduce audio-visual misalignment by creating samples for specific semantic concepts. As shown here, synthetically generated data can provide better audio-visual correspondence. Another major bottleneck is that existing methods are trained on no more than 144,000 samples, leaving scalability largely unexplored. This is because previous approaches have mainly focused on model-centric development. Recent advances in text-to-image and text-to-audio generative models have made scalable and highly controllable dataset creation possible. This enables the synthesis of samples for specific semantic concepts. In this work, we use synthetic data as both a verification and investigation tool to explore the potential of synthetic training for SSL. Specifically, we examine whether SSL models can effectively learn from synthetic data, analyze existing bottlenecks, and explore a path toward more advanced SSL models. This is the first scalable framework for training sound source localization models using synthetic data generated from text-to-X models. Also, this work proposed shifting the SSL paradigm from model-centric learning to data-centric learning. The overall framework is illustrated in this figure. First, we construct concept dictionaries for each VGG sound category. Instead of using only class names, these dictionaries contain more descriptive terms to improve diversity in image and audio generation. Since concepts may not be equally informative across modalities, we maintain separate dictionaries for visual and audio descriptions. For example, thunder in the night is visually informative because of the word night, but night provides little information for audio. This stage is performed by human annotators and is the only part of the pipeline that requires human intervention. On average, each class contains 3.35 visual concepts and 7.80 audio concepts. By using LLM-generated prompts for image generation and concept dictionary items for audio generation, we construct our synthetic VGG sound dataset. By using LLM-generated prompts for image generation and concept dictionary items for audio generation, we construct our synthetic VGG sound dataset. Now, let's look at some examples from the synthetic VGG sound dataset and see how the generated images and audio look and sound. Here, we visualize synthetic images from several random VGG sound categories. The generated images appear realistic and contain the target semantic objects. These are some audio samples from our synthetic VGG sound dataset for different VGG sound categories. Let's listen to a few examples. To human listeners, the generated sounds appear quite reasonable. But can AI models also understand these sounds the way humans do? We use recent audio captioning models to examine whether the generated audio contains the intended semantic concepts. The qualitative results show that the generated audio is semantically consistent with the target categories. This suggests that reasonably accurate synthetic samples can be created for large-scale dataset generation. After constructing the synthetic dataset, we evaluate whether self-supervised sound source localization models can effectively learn from synthetic data. We train a state-of-the-art self-supervised sound source localization model using our synthetic dataset. The trained model is then evaluated across various downstream tasks as shown here. Note that each task includes multiple evaluation datasets. We report the average performance across datasets for each task. The following results will therefore show average task performance. Detailed results for individual datasets can be found in the supplementary material of our paper. These are our experimental results using 144,000 training samples. By comparing rows A and B, we observe that synthetic data is already effective for sound source localization. Row C shows that pairing synthetic images with real audio is highly beneficial. This suggests that synthetic images help reduce audio-visual misalignment and noisy sample issues. Combining synthetic and real data makes a clear difference, even with a relatively small amount of synthetic data. Rows E and F improve performance across all tasks compared to the original setup. Row D shows that pairing real images with synthetic audio is less effective. We hypothesize that noisy visual samples and lower audio generation quality propagate errors during training. These results demonstrate that synthetic data, either alone or combined as synthetic images with real audio, can effectively train sound source localization models. After analyzing synthetic data at the 144,000 scale and identifying the key components of our recipe, we further investigate training beyond 144,000 samples, which has not been explored in previous SSL work. Row A shows that scaling fully synthetic data consistently improves performance and even surpasses training with real data at the 1x scale. Row B demonstrates that increasing the number of synthetic images while keeping real audio further boosts performance. Row C shows that combining real image-audio pairs with synthetic image-real audio pairs leads to significant improvements. We hypothesize that real pairs help reduce the domain gap on real test sets, while synthetic image-real audio pairs help correct noisy correspondence samples. Based on these findings, extending the real VGG sound dataset with large-scale synthetic image-real audio pairs becomes our final recipe, and a promising direction toward more accurate and generalizable SSL models. This chart summarizes the main experiments and compares the performance of different combinations of synthetic and real data. Here, we analyze which new categories the model successfully learns to localize, as well as which categories show performance degradation. We observe that the model newly succeeds on categories such as electric blender running and snake hissing. At the same time, some categories, such as playing cymbal, show degraded performance. Here, we analyze why some categories improve while others, such as playing cymbal, show degraded performance. Categories like snake hissing and electric blender running often contain poor visual samples in the real dataset, such as tiny objects or extreme close-up views. In contrast, synthetic generation can produce clearer and more informative images. However, for playing cymbal, although the generated images contain symbols, their visual distribution differs significantly from the real test images, where the entire musical instrument setup is usually visible. From this point, we present qualitative results of our model across different datasets and tasks. Thank you for your attention. See you at CVPR.